So when we are discussing this, x of z is equal to u of z into g of z. We are having this term a into z sine omega t by z minus e power j omega t, and g of e power j omega t can be, let us say, this is equal to m e power j theta, because it has got a magnitude and theta. Similarly, when we have e power minus j omega t, we have m e power minus j theta. Magnitude is the same and theta is minus theta. Okay, so that we can replace it here. When we can replace it here, mg e power j theta, we can substitute it as m e power j theta. G e power minus j theta, we can replace it with m e power minus j theta. Therefore, this is g e power j omega t by 2j into z by z minus e power j omega t minus g e power minus j omega t by 2j into z by z minus e power minus j omega t plus terms due to poles of g of z. Okay, so here when g of e power j m e power j theta, m e power j theta by 2j into z by z minus e power j omega t minus m e power minus j theta by 2j z by z minus e power minus j omega t plus terms due to poles of g of z. Terms due to poles of z of z. Now you can just have a combination of this. Common terms, if I remove it out, what do we get? M by 2j is common in both these cases, and I have e power j theta z by z minus e power j omega t minus e power minus j theta into z by z minus e power minus j omega t plus terms due to poles of g of z. This is x of z for us. Now applying inverse z transforms to this equation, what do we get? We have x of kt is equal to m by 2j into, what is the inverse z transform of z by z minus e power j omega t? It is nothing but e power j omega kt into e power j theta. E power j theta is as it is. Okay, so z by z minus e power j omega t, the inverse z transform of that is e power j omega kt minus e power minus j theta into e power minus j omega kt plus inverse z transform of terms due to poles of z of z. Now you have two different terms, and this is the response. This is our output response. Okay, when this is output response has both steady state response and transient response. The transient response is obtained by from these poles, the terms due to poles of z of z, and this is called our steady state response. So this is our steady state response, x of kt. So we only discuss xss of kt, which is the steady state response. You can discuss this xss of kt, which is nothing but m by 2j into e power j omega kt plus theta minus e power minus j omega kt plus theta. Okay, so what do we get here? M by 2j into, this is cos omega kt plus theta plus j sin omega kt plus theta minus cos omega kt plus theta minus j sin omega kt plus theta. So cos and cos gets cancelled, 2j and 2j gets cancelled, and we are left over with m sin, right, omega kt plus theta. So this is our steady state response. So steady state response is what we require here, right? So the magnitude m is given by modulus of g of e power j omega t, and theta is given by modulus of, angle of g of e power j omega t. And we know what is g of e power j omega t is nothing but, it is nothing but g of z when z is equal to e power j omega t. Okay, so this is what we are going to find out, the steady state response of xss of kt when it is m sin omega kt plus theta. So m is known, theta is known from the plant itself when you are replacing z with e power j omega t. Okay, so based on this we can also go for a few examples to find out the steady state response of the system. So we try to see what are the for a small system, let us say we are having x of z is equal to u of z plus a x of kt is equal to u of kt plus a x of k minus 1 t. U of kt is our input signal, x of kt is our output signal. Find xss of kt. Find xss of kt is what we require here. Now with this, the plant g of z is not given to us. Therefore, we can apply z transforms to this. It means that we will be having x of z. When you are applying z transforms to this, you are having x of z is equal to u of z plus a z inverse x of z, or x of z by u of z. What do we have? X of z by u of z, 1 by 1 minus a z inverse. 1 by 1 minus a z inverse, which is nothing but g of z. Output by input, which is the pulse transfer function. And since we are replacing z with e power j omega t, then this transfer function can be called as sinusoidal pulse transfer function. Sinusoidal pulse transfer function. Okay, when you are replacing z with e power j omega t, you are going to get sinusoidal pulse transfer function. Okay, so xss of kt, xss of kt, what is it that we are having, which is nothing but m sine omega kt plus theta. Now what is m and what is theta is what we will have to find out from this transfer function, pulse transfer function g of z. So what is m here? M is equal to modulus of 1 by 1 minus a z inverse when z is equal to e power j omega t. Right. So, or you can also call this as z by z minus c, or you can say that it is e power j omega t by, or you can simply directly put it in the denominator to find out this 1 by 1 minus a into e power minus j omega t, isn't it? So the modulus of this 1 by 1 minus a cos omega t plus a j a sin omega t, or we can have this as 1 by root over 1 minus a cos omega t whole square plus a sin omega t whole square, or 1 by root over 1 plus a square cos square omega t minus 2a cos omega t plus a square sin square omega t. A square cos square plus a square sin square is a square. Therefore, we have 1 by root 1 plus a square minus 2a cos omega t. This is the value of m. That is the value of m. And what is the value of theta that we will have? Theta is nothing but the numerator, it has theta. The numerator is 1, so the angle is 0 minus tan inverse of this, right? Or you can go with this one, a sin omega t by 1 minus a cos omega t, 0 minus. Therefore, theta is nothing but minus tan inverse. Therefore, what is xs of kt? xs of kt is nothing but 1 by under root 1 plus a square minus 2a cos omega t sin omega kt minus tan inverse a sin omega t by 1 minus a cos omega t. So this is our transfer function. Steady state response of this system, and this is how we are going to design the frequency response by finding out the transient response and the steady state response. Okay, after getting these values, we can use bilinear transformation and draw the border diagram to find the frequency response, where we can find out that is also applied based on the continuous time system. The Bode plot, whichever we have used there, the same procedure can be used for discrete time systems to find the Bode plot, and where gain margin, phase crossover frequency and gain crossover frequency can be obtained in a similar method that we have obtained in or used in continuous time control systems.